the much more complex example, I think a few full design that involve full design, full checking. Okay, but I will show it to you later. Okay, at this meanwhile, I want to concentrate to another checking. Yeah. Okay. Like I said last time, I think I stopped at moment capacity, moment check. Okay, we have done shear resistance, we have done shear buckling. Okay, this is the simple example that I've told you. Okay, and then I think I already introduced to you the bending moment resistance. Okay. Now I want to for today's I want to concentrate, to another checking, and we will perform one for one example. This good example. Okay. So bending and shear. So what is checking? Yeah, that involved in this particular case. Okay. Generally, um, a lot of cases will involve case where there will be bending and shear that occur simultaneously. What I mean is the forces the there's a maximum bending for first and maximum bending moment and maximum shear force occur at the same point. So you have to check, as a designer, you have to check whether the stress whether the actual stress exceed the allowable stress due to this I want to say as a combination of the bend shear force. So as in this slide, it said that bending moment and shear force acting in combination on structure member is commonplace. Is commonplace. However, majority of cases, the effect of shear on moment resistance is negligible. I put it this way. It is if if we have, let's say, one beam, and then being subjected to transverse load in the form of UDL load. When you do the analysis and you carry out the analysis, this is what's normally the GML and bending moment diagram and shear force diagram will look like. As you can see here, this is where the maximum shear force occur at the support, for the case of simply support beam. Simply support beam, and where the 0 point of shear force, this will indicate that there will be a maximum force or height bending moment occur. So at this point we will have maximum bending moment, but zero shear force. This is quite normal. Or maybe second case. Let's see second case. Or sometimes we have another additional forces acting on the beam, and then you will get something like this. Still at this particular point, you have VED. It might not be the shear maximum. It might be not the shear maximum. But, okay, but in this situation, you have to check because due to this combination, where it's acting simultaneously at this specific location, okay, we need to assess. We need to assess whether, okay, whether these two response or these two forces, okay, will resulted in the uh, material stress. The material stress might be exit the allowable stress. Okay, I don't want to say material stress. Stress, we just say stress. Whatever stress, maybe due to the material, maybe to the forces. Okay, okay. Stress will be allowed. Will be exit the allowable stress. Okay. So in this case, you need to assess first. Okay, whether the VED here is low or high. If it normally it is low, okay, if it, okay, you encounter the case where the VED here is considered high, okay, what you need to do, okay, is to reduce the moment capacity. Reduce the moment capacity. Okay, remember that for shear force, for shear force, okay, okay, for shear force, the applied shear force here, let's say this is the maximum shear force at support. You need to compare with the shear capacity, the VCRD. Okay, normally without the torsion, the VCRD will be the VPLRD. I have already explained this one. If you still do not understand, you can ask me later. Okay? Okay, VPLRD. Oh, okay, that is the first thing. And the M maximum or the bending moment maximum or MED, the applied moment, you need to check with the moment capacity, MCRD. Okay, MCRD. But for this case, if VED have been found here as a height shear force acting at this point, at this maximum, where the maximum moment occur, so what you need to do is you need to reduce the moment capacity that you initially calculate. You need to reduce, okay? So, okay, let's us refer to Eurocode. Okay. Okay, where shear force is present, okay, as I drawn here, okay, allowance should be made for its effect on moment resistance. So we need to check its effect. So how? Okay, this is how we check. We need to define whether the shear force is categorized as low shear force or high shear force. Okay, if it is high, okay, there will be another procedure that you need to consider. Okay, where the shear force less than half the plastic shear resistance, its effect on moment resistance may be neglected. Means that, again, this is how you need to assess. How to assess? It said that if the VET is less than half or 50%, okay, half the VPLRD, so you can ignore the effect. So means that if ED is bigger than or exceed the 50% of the VPLRD or half of the VPLRD, this is what you need to do. You need to I will put it like this. I will recalculate the moment resistance. I will recalculate the moment resistance. I'm not using the same symbol. Okay, I will not using the same symbol. I do not want you to get confused. Okay. Okay. Except where shear buckling reduced in the section resistance. Okay. This one is about shear buckling. Okay. This one is not applicable if you need to reduce shear buckling resistance. Okay. Normally this one will not happen if you use standard section. Okay. Rarely happen if you're using standard section. Normally standard section will have higher shear buckling resistance. Okay, so otherwise, otherwise means that if shear buckling is bigger than half of this plastic shear resistance, I mean, if you encounter this situation, it said the reduced moment resistance should be taken as the design resistance of the cross section. It said cross section. This is cross section resistance, right? Remember, I told you we have two checks: cross section resistance, buckling resistance. MCRD is cross section resistance, clause 6.2. Buckling is clause 6.3. Okay, so it said that you need to reduce the moment resistance. I mean it means that the design resistance of the cross section means that this one. Okay. How to reduce? It said by calculate using reduced yield strength. How to reduce? One, calculate reduce yield strength. Means that reduce the Fy. You need to reduce. Okay, how to reduce? You need to calculate the rho here. 1 minus rho multiplied by F1. Okay, where rho is this one. Okay. When torsion is present, then you will have another equation in order to calculate rho. Okay, and then if you go forward, okay, there's a more explanation. Okay, here in bracket 5, the reduced design plastic resistant moment allowing for shear force may alternatively be obtained for I cross section with equal flange and bending major axis. You have another alternative method. Okay, alternative method. But this alternative method comes with syarat with a certain condition. What is the condition? Okay, this one is for I section, but equal flange. Actually we have another I section having wider flange at the bottom. It's still I section, but having wider flange. So for this case, you cannot use it. Okay. Okay. So the alternative here, as explained in bracket 5, okay, is for I section with equal flange, and the bending is about major axis. Means that if you arrange your beam, the arrangement is like this. Okay, transverse force, will create bending moment about y-axis. Then this is allowed, okay, for this alternative method. So means that if you are using if you fulfill this, okay, then you can use the alternative method. So you can directly calculate the new moment resistance based on MYVRD. Means that, okay. So for alternative method, what you can calculate MYVRD. Okay, otherwise you can just reduce the yield strength. That's all. You can use the strength. Okay, remember MCRD. What is the formula for MCRD? It depends on the section classification. Yeah, but okay, this one. Yeah, see FY. You need to reduce the FY. If you are using for the first method. Okay, the second method is the alternative method, but alternative method comes with certain condition. Okay, so okay, boleh faham I think this note is complete. Okay, for the case where applied shear force is greater than half, okay, of the plastic shear resistance, moment resistance should be calculated using reduced design strength for the area. This one. Okay. VPLRD may be obtained from clause 6.2.6. When torsion is present, it should be replaced by VPLT, torsion here, RD. If torsion present, okay, an alternative to reduce design strength for the shear area defined by equation 6.29 means that this one, reduce the yield strength. You can opt for another equation where you can use MYVRD. Yeah. But it will okay, the alternative reduced design strength for shear area defined by equation that involve calculating rho involves somewhat, it said, tedious calculation. I've never performed that calculation because normally I will opt for second option, alternative method. Okay, but it said it tedious. It might be tedious. I've never tried. Okay, it might be tedious. Okay, tedious calculation. Okay, so equation, that tedious equation may be a which involves somewhat tedious calculation. Okay, alternative, an alternative to the reduced defined by equation 9. Okay, it's okay. It said that in this statement, it said that it is tedious calculation if it is involved equation 6.29. Equation 6.29 is the expression calculating rho, rho, value of rho. Okay, so this is alternative equation 630. Equation 630, it said may be applied to the common situation of I section equal flanges subject to bending about the major axis. In this case, reduced design plastic resistor moment allowing for shear is given by this expression. This expression. Okay. Okay, still involve rho. Yeah, still involve rho. Okay, now I'm confused. If it is still involve rho, where is the tedious part? Don't think it's quite tedious. We're using the same equation in calculating rho. This one is just 1 minus rho Fy. Dia tak rasa tedious lah, I think. Dua-dua okey. Okey, sekejap MCRD. Okay, it's okay. Let us try. Okay, the examples. Okay, let us try. Then we can judge whether it is tedious or not. Okay. Okay. So. Okay. Let's see example 3.3. Not sure whether you have this example in your module. I may have changed some of the example, but since I already give to you the PDF file, so you can have various examples. You can have more examples, okay, that can help you to understand. Okay, so let's see this example. Okay, in this example, okay, we have short span beam, just 1.4 meter, but it is simply support beam. It said laterally restrained beam. Okay, so for laterally restrained beam means that restrained beam, restrained beam. So if it is restrained beam, we do not have extra checking that we need to perform, but still have a lot of checking that we need to do. Okay. And then it carry a point load at the mid span. Okay, a point load of 1050 kilonewton at its mid span. Okay, the arrangement. Okay, so based on this, based on the loading, okay, if you perform the analysis, this is what you will get. This value already given in this example, okay? Okay, but you need to perform the analysis. Okay, it's quite simple, Simple kan? Yeah. 1050 kilonewton, simply support. So this one should be W over 2. Assume this is the design load. So this is what you will get. Okay. This one W over 2, 1050 divided by 2, of course, 525. 525. And then the area here is the value for MED, moment maximum, is given already, 367.5. If I consider the area, okay, 525 multiplied by 0.7 should be equal to, siapa tak tahu buat, dia belajar balik 367.5 kilonewton. Okay, but it's already given, the value is already given. So VED 125 kilonewton, MED is 367.5 kilonewton meter. Okay, we need to check. So VED, we need to check with the VCRD. MED, we need to perform MCRD calculation. Okay, I'm using Eurocode. I think it is good move if we refer to Eurocode directly. Okay, we know that VED, this is what we need to fulfill, what we need to satisfy to ensure safe design. Okay, ensure the safe design. The VED, VCRD, the ratio of VED, the VCRD should be less than 1.0. Okay, there's no torsion here. We do not have much information regarding the other load acting on this beam. So the only force acting on this beam is coming from transverse force, 1050 kilonewton. That's all. That's all that we know. Okay, so there's no torsion, so VCRD will be VPLRD, and it can be calculated from this expression. AV Fy divided by square root 3 divided by gamma m naught. Fy, we do not know yet. The Fy, do we have another okay, we have another information. We already have the size, 406 times 178 times 74. I think in order to get the properties, we need another information, we need another data, we need another properties. So we need to refer to Blue Book 407, right? 407. Okay, this is properties. This one is dimension. So 407, mana tak ada pun? Sorry, maybe not 407. 406, sorry. 406, 178 times 74, right? This is the size. Okay, that is the size. Okay, then what we need? We need to determine Fy. So for Fy, first of all, I need to refer to table 3.1. From table 3.1, we should check the thickness. What is the thicker thickness? I always said refer to thicker thickness because thicker thickness having less yield strength. So it will put the structure in severe case. Yeah. Okay. So the thicker thickness, we have thickness for web, thickness for flange. So between these two, the thicker one will be the 16, the flange, 16 mm. So 16 mm obviously is less than 40 mm. So based on table 3.1 for steel grade S275, the Fy will be 275 Newton mm squared. Okay, done. So just one unknown left, which is AV. So what is AV? AV is said here. AV is the shear area. Okay, I'm using roll I section, so I need to use this expression where A, okay, so we need to calculate the AV. Okay, AV is given by A. We do not have AV yet, okay. Just say A minus 2BTF4 plus thickness of web plus R multiplied by TF. A means the gross area. So what is the gross area for this size? Okay, so gross area. This is surface area, not the gross area. So we need to check in another table, which is properties. So this is the area of section. Size 406, 178 times 74. The area of section is 94.5. Okay, 94.5 centimeters squared. You need to convert to millimeter. Okay. B, what is B? B is the dimension for width. Okay, for width. So you can get from this table too. Table of dimension, not the properties, table of dimension. What is the width? Width is 179.5. 179.5 mm. Thickness of flange. Thickness of flange here is 16. We have seen before. We have checked previously. Okay, in mm. Thickness of W means thickness of web is 9.5. 9.1. What is R? R is the root radius of the beam. Root radius here. Okay, root radius is 10.2. Okay, thickness of land is 16 mm. Then you need to calculate. Yeah, you need to calculate. Okay, refer again to Euro BS. It said, but not less than eta HWTW. All this, the result from this expression is said, but not less. Don't less. It should be bigger. Not less than eta HWTW. Okay, eta you can assume as 1.2 or 1.0. HW is height of web. For this case, you need to calculate manually. There's no data in the table of dimension and properties. Height of web is referring to this height, the web height, where the total height here, H, minus thickness of web. We have two thickness of web. That is height of web. Okay, thickness of web, we have that already, 9.5 mm. Okay, total height, okay, again refer to table of dimension and properties. Total height 412.8. Okay, 0.8 deduct with 2 times thickness of web. 9.5. So HW, okay, you can calculate. Eta, we have that eta. Okay, just make sure, you don't have to make sure. You just have to evaluate whether it is bigger or less than eta HWTW. That's all. Okay, so what is the result? Okay, so for this case, okay, the value from this expression is equal to 4,184 mm squared, while eta HWTW is 4,341. Means that the result from this expression, yes, it is less, which is, it's said but not less, but now it is less. Okay, how to put this one? Okay, the result from this expression is 4,184. And obviously, it is less than what we get from eta HWTW. Okay, from Eurocode, it said that this result should not less, but not less. Should not less, should be bigger. So since it is not fulfill what the statement here, so what we need to do is AW, okay, you should take the value from eta HWTW calculation. It is like this represent the minimum value of AV, the minimum value that you need to use for AV. Okay? See? Okay. In this case, see? So AV, you should take as 4,341 mm squared. So just substitute this value into this expression. Yeah. So VPLRD is 4,341 mm squared multiplied by 275 Newton per mm squared divided by square root 3, and all this divided by partial factor of 1.0. Then you can get what is the shear capacity. shear capacity. In this case, shear capacity is 689.2 kilonewton. So this is the capacity. What is the applied shear force? Applied only 500 means that capacity is bigger than the applied shear force, which is okay, certified. That is what we need. Okay, that is what we need. Okay, we're done with shear resistance check. Okay, can we calculate? Can we assess? Can we check for the moment? Okay, yes, we need to perform the moment check too. MED 360 apa? 67 0.5 kilonewton meter. Okay, so refer again. You refer back to Eurocode for moment, for bending moment. This one is shear. For bending moment, this is what you need to fulfill. And you have 3 equation. So which one you need to use? It depends on class. So since it depends on class, you need to perform section classification. You need to classify the section. Okay. So how to classify the section? Table 5.2. Using table 5.2. Okay. I hope that you take this chance to make sure that you understand how to perform section classification. We did a few times already. To those who still not understand, please concentrate on this one. Okay, what we have now? We have beam. We have I section. And this I section is being subjected to concentrate force at its mid length. Okay. Based on this beam arrangement, the orientation, based on orientation, kedudukan dia macam you letak. So this force is a transverse force that results in bending moment around its major axis. This is what the force will do to this structure, to this beam. Okay, bending, rotate about the major axis. Okay, so for section classification, okay, based on table 5.2. Okay, from that table, okay, what we need to do? Okay, we need to classify for each element. For I section, we have 3 elements. 1, 2, 3. Since we are using standard section and equal flanges, so I just need to check one of the flange and the web. That's all. So just 2 elements. Okay, because the bottom flange is similar to the top flange. Why we need to perform twice. Okay. So let's say we check for web first. Web. Second element here. Web is the internal part. Why it called as internal part? Because fix. Okay, at its both end. Yeah, fix. So we have diagram here. Okay, so I sections. Okay, you can use. So means that based on this diagram, based on this diagram, I and H section can be used for this table, sheet 1 of 3, this table. Can we use this table for angle? No, we can't, because there's no diagram for angle here. So we cannot use. We can use for I or H section, roll, see, here, this is picture of roll. This one, I or H section for build-up section. Why I call it as a build-up section? Because, see, this is symbol, I said symbol for well. See the triangular with Okay, black triangle here, it means welding. So we have three plates, and then we form I section or H section based uh, by welding all these plates together. Okay, so this is uh, build up section. This one also build up section that form the rectangular shape. This one row section because there's no welding here. There's no. It's the smooth. We have quite smooth corner here. Yeah, smooth corner here. Okay, based on the radius. Yeah. So that is what the diagram means. Okay, back to our case. We are using I section, so we can use this table. Okay, which column that we need to refer? We have three columns here. Okay, part subject to bending. Okay, I'm referring to this one. This is for internal part. I said internal part here is wet. So based on this case, yeah, this beam will bend. Okay, I said when it bend, okay, when it's bend, just due to this point load, web will experience bending and the top flange will experience compression. We care less about this one because this one experience tension. Tension will not create local buckling. So you do not need to be afraid because local buckling is the I said one of the failure mode that we need to tackle. So web will experience bending. Okay, then referring again to this table, okay, means that the part subject to bending. So for class 1, okay, C over T means that C over T actual, if it is less than 72 epsilon, it means that you fulfill class 1. What is the C over T actual? You can do it manually, but since I'm concentrating on using only section from standard table, so I will refer to whatever data that I can get from Blue Book. Okay, so for C over T, for web, right? For web, okay, where is the size? Okay, this is the size. Okay, for web, okay, the C over T ratio is 37.9. The actual value is 37.9 compared to 72 epsilon. I do not have the value of epsilon yet, but don't worry. Refer again to this table. Okay. Fy is 275, then epsilon value is 0.92. So we can directly get the value 0.92. If it is 0.8, it's still bigger than 37.9, right? You congak aja boleh tahu. So definitely it's less. So means that the web, we check for web in or is class 1. Class. Okay, that is web. I said section classification, we need to perform for all element. Yeah? Okay, the second element is flange. Okay, second element is flange. Flange, we call it outstand flange because one end is fixed, the other end is free. I refer to just one side because this is where your C lies. C, we need C. C is measured from here to here, not the whole width. Okay. Okay. So outstand flange. Okay. Refer again to the Euro code. Okay. But now we need to proceed to table or sheet 2 of 3. This is meant for outstand flange. For class 1, okay, flange. Flange, we concern the part that subject to compression. not tension. Okay, compression. So the top flange. We concentrate on the top flange now. So compression on the top flange top flange experience compression. Okay, so means that part subject to compression. So the C over T, means the C over T, the actual C over T for flange element, flange element. This one is for web, means that here, this is for web, this one element for flange, means that this rectangular, okay, this rectangular, okay, okay, should less or equal to 9 epsilon, then it can be said as plus 1. What is the actual C over T ratio? Okay, refer to blue book, then you can get the data. Okay, C over T for flange, 4.68. 4.68, okay, compared to 9 epsilon, 9 times 0.92, 9 times 0.92, okay, this will be the 8.28, which is obviously less. Then means it is fulfill the maximum value to be classified as class 1. Okay, so since web is class 1, flange also class 1, then the overall class for this section, the overall section classification for this particular size is class 1. Okay, now we know this section is class 1, so we can use equation, bending moment equation that is designed for class 1, where the expression, where the MCRT is equal to W plastic times Fy divided by gamma M, I think M2, M naught, sorry, M naught, okay. Okay, what is VPL? WPL? WPL is modulus plastic. What is the value of modular plastic? That is what we need to refer from the table of section, standard table. Okay, WPL. Okay, WPL. W is modulus plastic. We have Y and Z. I said last time, refer to where the bending moment occur. In this case, the bending moment rotate about Y axis. So I need to refer to WPLY, not Z, because this bending moment is bending moment at Y axis. Yeah. If you check for Z axis, make sure this MED rotate about Z axis. Then you can use WPLZ, not Y. Okay. So WPLY, okay, WPLY is 1,500 centimeter cube. 1,500 centimeter cube multiplied by Fy. Fy, we have Fy 275 Newton per mm squared. Gamma m naught is 1.0. Then you can calculate the value of moment resistance. Here is the plastic moment resistance. Okay. So please refer to whatever value that have been calculated from this example. Do not worry. I know this one is 1501. Like I said, it will refer to another table. It's, you know, just the because of maybe the value, the initial calculation, they do rounding, or it is rounded, rounded. Betul lah rounded, dia apa, betul lah rounded, kan, bigger than 5, then you can add 1, okay. Okay, 1000, you can use 1500, don't worry, okay. Convert to millimeter because here, or maybe you can convert to meter, don't worry, this one also convert to meter. At the end, normally for moment, we need the moment to be in unit kilonewton meter. Okay, so the result is 412 kilonewton meter. Okay, then you need to compare, or you can do the calculation, the ratio, you can perform the okay, you can check the ratios. 367.5 divided by 412. So obviously it is less than 1. This is acceptable. Safe for moment resistance. Okay, what is the other checking? Okay, we have another check. If you do not remember, don't forget you have book Eurocode. Okay, you have Eurocode, so you can check what is the other checking that you need to perform. We have done shear, we have done bending moment. Okay, for shear, we do not forget we have another information in this particular clause. Okay, in the same clause, it said in addition, the shear buckling resistor on web without intermediate stiffener. Okay, in our case, the web, this section, the web, okay, we are not using stiffener. Stiffener is a plate actually. It welds to the flange, to the web. Okay, we have plate. Okay, plate here. The purpose of this plate is to strengthen the web because the web is quite thin, right? Just 10.5 millimeter. Under high shear force, this could bend. Dia boleh buckling. Okay, sometimes you need plate to strengthen the web. Okay, in this case, we do not need, let's say we do not provide the stiffener. So for that case, the Eurocode said for web without intermediate stiffener, we should check for shear buckling resistance. If this thing happen, shear buckling resistance only need to be checked if the ratio of HW to TW is bigger than 72 epsilon divided by eta. You need to check for shear buckling. And the checking will involve another clause, Section 5, Eurocode 3, Part 1, 5. It said Section 5, EC3, Part 1, 5. Okay? So let's check whether we need to calculate the shear buckling based on this clause or not. Okay, it said HWTW. Okay, check the HWTW. Kita dah calculate tadi kan? Lupa. What is HW? HW is H minus 2 times thickness of web. Where is the calculation for HW? HW. This is the value of it. 380.8. 380.8. Thickness of web, I think 10.5. Ke 9.5? 9.5, sorry, 9.5. Sorry, it's 9.5. Okay, so what is the value? 380.8. Student yang rajin, dia akan calculate tanpa saya, cikgu yang calculate. Okay. 72. Okay. Epsilon 0.92. Eta, let's assume as 1.0. You can take 1.2. Yeah. It depends on the national annex. Eurocode allow you to choose. Okay. Eurocode give you 1.0. BS 1.2. Okay, so what is the value of this one? 72 epsilon eta. 72 times 0.92. This will be 66. So this is 40. This is 66. Means that in our case, HW, TW is less than 72 epsilon eta. If it is less, there's no further need for shear buckling check. Okay, let's stop there. Okay, so we do not need to check. No need to check. Okay. Okay. And remember, for this case, we have shear force acting at the point of maximum force. Acting at the point where the maximum force occurs. MED. This is VED. This is also VED. In fact, maximum, right? In this case, yeah. In this case, yeah. So, Eurocode said that bending, if bending and shear acting simultaneously, we need to check for this one. Clause 6.2.8. Okay. Okay. Clause 6.2.8 bending plus shear. Okay. Oh, sorry. Bending say bending plus shear. So to justify whether to clarify whether shear force is low shear force or high shear force, okay, it said that VET compare with the 0.5 BPLRD. We have this value because we already calculated that. VED, we have 525 kilonewton. 0.5 VED, VPLRD, what is the value of VPLRD? VPLRD, $689.2. Okay, so 0.5 times 689.2. Okay, this one is equal to 344.6. See, VED now is bigger than 0.5 VPLRD. For this case, Eurocode said that, yeah, okay, if it is less, okay, otherwise, since it is bigger, so we need to reduce the moment resistance. In this case, I will use alternative method because I'm using I section with equal flange and the bending about major axis, which is the y axis. So I will calculate MYVR. Okay, I think this time I want to refer to my slide. Okay, I just want to have okay to save the time. MYVRD. This is the equation. Okay, this is the equation. Okay, what is WPLY? This is plastic modulus at y-axis. Remember, 1,500 centimeter cube based on our table. But in this solution, it's using 1,401. Okay, doesn't matter. Rho. We do not have rho. AW means that the area, A is the area, W is web. So the area for web, how to calculate area for web? Okay, easy peasy. This is the area for web. Means that the height of web multiplied by thickness of web. We have height of web. AW is HW times TW. Ada tak sini? This one. We have this one already. Thickness of W, thickness of web is 9.5. We have checked previously. So calculate and you will get this value. Okay, we have that. Thickness of web 9.5, Fy 275 Newton mm squared. This one is mm. AW is 3,000 mm squared. Okay, and then you need to power of 2. Okay, rho, what is rho? Rho is given in this equation. 2 times VED means that the applied shear force. The applied shear force in this case I'm using the applied shear force here, not here. It's just that kebetulan, kebetulan dia sama. Okay, it's just that in this case, it is the same value as here. Okay, because sometimes we will have another value, right? Different value for this case, but we need to check where the shear force acting together at the maximum moment, at the point of maximum moment, acting together, acting simultaneously, dia berlaku serentak. For this case, for this point, yes, we have VED maximum too, but our moment is 0. It is not significant. This one is much more severe. So it is significant to check at this point. What are the stress? It could be the stress over the stress limit. So that's why we need to check. Yeah. So in this case, it's proven that we need to reduce the moment capacity. So, okay, now we need to calculate rho. 2 times VED. VED is 525 kilonewton. VPLRD we will recalculate 689.2 minus 1 and then bracket power of 2. Okay, so rho is 0.27. This one is 0.27. Substitute all this value into this expression and then calculate. Okay, you have another things that you need to aware. Need to be aware. This one. It said this value should less or equal to MYCRD. What is MYCRD? This one is actually MCRD. Y here is stand for bending moment that you assess, that you menilai based on Y axis. Based on Y axis. Okay? But it is in MCRD. So do not get confused. Okay, why it should less? It should less. Of course, it should less because this one stand for what? Reduced moment capacity. How come it can be called as a reduced moment capacity if it is bigger than the moment cross-section capacity? Right. It's said that as a reduced moment capacity. You need to perform this checking by reducing the moment capacity. So it should less or equal. Okay, so when you calculate, this is what you get. In this case, it is less than MCRD. So this will be your new moment resistance. No more this one. This is the new moment resistance for sorry, not less lah, bigger. Sorry, it's not less. Sorry. This is the sorry, sekejap. Kita perlu check Kita check. We need to check again. What is the value of MCRD? MCRD. Oh, MCRD 412. Okay, good. MCRD here is 412 kilonewton meter. This one, of course, less than MCRD. Then I said this will be your new moment resistance. Okay, and this new moment resistance, MYVRD, should compare with the applied moment. Again, you need to compare with the applied moment. Applied moment, (367.5 kilonewton meter). Okay, MYVRD is 386.8 kilonewton meter. Okay, good. You still have resist strength, even though the gap is just 20 kilonewton, but still it is safe. Okay, then this one is accepted. Okay, it is safe in terms of moment check. Okay, what else? That's all. That's all. Okay, deflection. Okay, guys, we missed one lecture because tomorrow will be holiday. I need to replace the class. We do not have much time. Okay, the other class, they already finished design. I should finish beam design by this week, but I lost one class. Can we replace the class? I think we need. Not can we? I cannot ask you like that. We really need to replace the class. Okay. Okay. So I will do the. You need to vote. I need to do poll. To get your jawapan lah. Okay. Okay, we try to finish this one. Okay, before that, okay. Author. Please access your author. I prepare one. I have prepare two. Already prepared to. Actually I prepared two question, but the other one I think it's not been saved. Okay. Just a simple question, really simple question. I'm giving you 10 minutes, okay? not 10 minutes, 9 minutes until 3:30. Okay, until 3:30 for you to answer this one. Today, 3:30. Okay, please access. Okay, please access. Meanwhile, I create another question. Yeah. I have total student of 47, but online, but I have online only 41. Yang mana lagi orang? Memang tak berminat ni. Okay, sila jawab Senang je. Dah belajar dulu-dulu analisis je pun Belum design lagi. Okay.
Sorry, Doctor, I can't submit my answer.
Huh? You cannot?
Can't
What?
submit. Mm-hmm.
You cannot what?
Doktor, dia memang time tu time's up Maybe
Yep.
sebab tu kot tak boleh nak submit answer.
Kenapa times up? Saya buat 3:30 kan? Ke salah?
Tak sure lah doktor. Saya tak perasan tadi.
3. Okay, jap. Okay, 3. Oh, okay. Saya tak set yang dekat assessment. Saya tak set dekat assessment. Saya set dekat stream je tadi. 3:30. Update. Okay, boleh tak anda? 3:30. Boleh hantar tak? Okey tak? Saya tak perasan. Okay. I ask you to show you yeah.
Dia memang tulis dekat chat box tu je.
Checkbox je lah. Sebab
Okay.
sepatutnya saya set you boleh upload tapi saya terlupa nak set. Just give me the value.
Value answer ke calculation, Doktor?
Tak payahlah, calculation you kena upload tapi tak boleh upload. Saya tak setkan you boleh upload. Saya kena setkan dulu. Tapi tadi saya tak buat. Saya lupa nak buat ni.
Okay, Doktor. Thank you.
Hantar jawapan je. Okay dah Okay, saya nak proceed kepada satu lagi checking. Okay. Deflection check. Okay, in Eurocode 3, deflection of I think you already know deflection check is serviceability check. What is serviceability? What is ultimate? I don't think I need to repeat that. Okay. So one of the serviceability check or or SLS, serviceability limit state. The checking also involve deflection check. Okay, so excessive deflection will contribute to certain failure like cracking on your finishes, on the brick wall or the plaster. And based on UK National Annex, this is UK National Annex, not Malaysian National Annex. Okay, deflection check should be made under variable action. But in Eurocode, we have another approach. Okay, before that, for serviceability limit check, so we have vertical check, we have horizontal check. But for horizontal check, that is for frame. Okay, frame. We tackle about beam design, so the deflection that involve only vertical deflection for that element. Okay, so for beam, for beam, okay, this is the total deflection. Also, deflection due to the same weight, deflection due to the imposed load on top of the beam. Okay, but the point is, in this checking, is that the actual deflection should less than the allowable deflection. Okay, we need safe design, so we need to verify whether the actual deflection bigger or less than the allowable deflection. Okay. In this table, it is about load combination or combination of action that you need to consider during the deflection check. Okay, during deflection check. So if you are if the combination is characteristic combination, the permanent action for unfavorable, this one is favorable. This is the variable load, the leading or the other. You need to assess this one. You need to perform the calculation based on this. And then that will be the design load. The design load for deflection check. Then compare with the design situation with the design limit, the deflection limit or the allowable limit based on specific element. If it is cantilever, this will be your deflection limit. If the check is for beam that carrying brittle finish or plaster like the floor beam, then this will be the allowable limit for that structure. Okay. This is about horizontal deflection. Like I said, this is about the frame. Okay, I skip this one. Okay, another thing. This is based on Eurocode. Based on UK National Annex, UK National Annex allowed us to consider only variable load. No need for this load combination. No need. That is based on UK National Annex. Normally, Malaysian National Annex follow UK National Annex. Okay. Okay. See this one. UK National Deflection check should be made under variable action. Okay. And UK National Annex said unfactor variable action means that 1.0 QK. Okay, 1.0 QK. Okay, I just want to raise my concern. In the middle checking of all the quizzes that I already give to you so far, and I found that I would say 100% of you do not understand about load combination. I do not know how can this happen. You should already gain that knowledge during design structure. If you are not satisfied, I allow you to make comments. I do not know what type of comment that you want to raise, but I I need you to know that you need to have that kind of knowledge first before entering this course. I do not have time to teach again what you should have been told or what you should have been teach. Okay, I do not know where that mistake coming from. You are the one who you are the one who need to to investigate, or you need to know why you do not understand. I do not want uh, to to be I don't know, I do not want to be part of that that process. The thing is, what you need to know is that you should know what I meant by 6.10, 6.10A, 6.10B. Okay, in my module, I have one example that tackle that problem. And um, and there is one example too from concrete design subject, using one of the reference, not IR Saleh. I think the other book. I do not know who is the author. I do not remember the author. But there is a one example using load combination, showing how to use load combination, and that example is based on water tank. That is good example. How can you um because actually you as a designer, who the one need to define which combination will create will create case severe load case from various. You can have a series of load cases, not only one load cases, where you combine this and that. Okay, which one will be the partner? Okay, that water tank example is one of the good example, but you still can refer to my module. I have one example, okay, where we have uh, 3 variable action. Why is said leading? Why is said leading? Because you can change. Yeah, maybe certain situation, the wind will be the leading variable action. So you put the wind load as a leading, the other variable load as others. But for one equation, do not exceed 2 variable action. Even though you have 3 variable action, you need to alternately. You can use them alternately. Okay. For case 1, for case 2, it depends. Depend which variable action or which load that you think will put your element into severe case. You can have various approach, you can have various combination. That's why you can have a few load case. I'll show you. I just show you. I do not have that. Uh, okay. We should do this one. Equation 6.10, I clearly said in my question. 6.10, 6.10a, 6.10b. Okay, this is the example. Okay, this is a good example. See, I have 3 variable load. One is variable load from the roof. Second variable load from wind. Wind, we have 2 type, uplift and downward direction. Okay, and then the third variable load is no load. So I said you should consider not more than 2 variable load in one equation. Okay, see this one? Only 1 variable load. This is typical. We've seen this much in example. Why? Because in example, we can't do length. We do not want lengthy example, lengthy equation, right? Lengthy calculation. Okay. This load case, we have 1, 2, 3, 4, 5 load case. Just for example, to show how to consider equation 610, 610a, 610b. And if you want to include this in design, better you do in using software. In the software, you can create load case 1, load case 2, load case 3. Where are the loads coming from? This load combination. But from from the quiz that you already answer, I can say so far 100% do not answer my question. They either only perform 610b or just typical solution using 1.35 DK plus 1.5 QK. I do not know why you cannot do that. You cannot do. I do not know. You cannot do, or you do not understand. I'm not sure. That's concerned me, because you are in your final year. How come your load is not correct? Macam mana loading masih tak betul? Ni sekarang dah belajar design. Macam mana? You ask yourself. Okay? Kalau awak seorang yang rajin, awak cari solution dia. It's just that I cannot spend my time to teach you what you should have learned or you should have mastered. Awak dah kena master subject tu. Okay, last example. Okay, deflection. Okay, we have simply supported roof beam. Okay, so digest this. Roof beam. Imagine this is a beam supporting roof. Means that if you have like this skeleton, the building skeleton, so this is the column, and then another column. Okay, say this is 2-story building. Okay, this is the footing. Okay, so this is roof, and then this is the roof. I have 2 okay, I have 3 trusses. Okay, so let's say I'm designing one of these beam. That's why I said this is roof beam. Okay, so this roof beam, okay, it is simply support with span of 1.6 meter subjected to the following loading. This is unfactored load. This is characteristic load. Okay, the dead load is 8.6. The imposed load on the roof, 20.5. Snow load also, of course, snow duduk kat atas roof. Okay, the snow load is 1.8. Okay, now the question is not about uh, uh, it's not about design the beam, but it more like for you to determine what is the suitable size. Means you do not have the size yet. So far you've been given the size and then you do the checking, right? For this example, you are the one who need to propose the initial size. Okay, first, I can we do not have size. Okay, how come we check for the deflection? We know for deflection check, you will compare the actual deflection versus the deflection limit. In this case, we do not have the size. Okay, so what I will do for the safe design, I know that the actual size should less than this limit, right? Or worst come to worst, it can be equal. Okay, so I choose the severe condition where the actual is equal to the deflection limit. I know that my case is simply support beam, and that simply support beam carry UDL load. Okay, carry UDL load. Carry UDL load. Okay, kilonewton per meter here. Carry UDL load. So for UDL load, okay, based on table 3.4, okay, based on table 3.4, for UDL load, the maximum deflection, or this one is actual deflection due to the loading. Okay, for simply support with UDL, okay, the actual deflection can be calculated based on this expression, 5 divided by 384 capital W power of 3 divided by EL. This is equal to deflection limit. For the case of deflection limit, I can choose, okay, I can choose the other beam, span over 200. I can choose the other beam as L over 200. Okay, I have load. Yeah, so means that I can calculate my design load. The capital W, which is should be in kilonewton, okay? This one capital W. So the value of loading should be in kilonewton. E, I can assume I'm using typical steel with the value of 210,000 Newton per mm squared. But for I do not have that value because I is second moment of area based on size. I do not have size yet. So this will be my guide. Okay, so I need to determine I required. I need to determine the initial size. So I need to, this is the only unknown. So that is I will be the I required. Okay, so for I required, so rearrange this formula, you will have this one. Can you notice this? Small w, L power 4. It is because it using small w in unit kilonewton per meter. I'm using capital W unit kilonewton. That's why I can multiply with L power of 3. Okay. This is just a simple mathematics. Okay. I do not need to teach you. Okay. So W. Based on Eurocode, okay, if we base on national annex, UK national, UK national annex, I can take only QK, unfactored load. But based on EC, I need to do the load combination. Okay, I need to do the load combination. Okay, based on this one. We do not know which one will be the leading. That's why I said you can alternately change. Snow load can be leading, and then the second case, the roof wearable load can be the leading action for wearable load. Okay, I do not want to have case 1 and case 2. Okay, I'm using whatever been written here. Okay, the W here is GK, unfactor 1.0 GK, but it is load combination based on Eurocode. This solution is based on Eurocode, not UK National Annex. If it using National Annex means that the W here just take QK, that's all. QK, no GK. Okay, so since we have 2 QK, I think this is good for us to consider Eurocode approach. Okay, 1.0 GK plus 1.0 QK, 1.0 GK, 1.0 QK plus I do not know how to call this. Okay, this symbol I forget. Okay, is it psi? Psi ke? Okay, psi kan? Psi naught 1 multiplied by QK1. Not the leading action. In this case, if I check, okay, in this case, the leading action is this one, leading action, which is it consider roof variable action as the leading action. It is obviously can be the leading because it is 20 compared to 1.8 kan, 1.8. Okay, and then the other variable action is snow. In this case, it is snow. Snow is 1.8. Okay, this one based on the altitude. Okay, so you should check the table. We have table in Eurocode. It is 0.7. All are unfactored load for serviceability check, not using partial factor. So sum up all this value, you get 30.36 kilonewton meter. That's why it is small w. Okay, small w. Okay, so let's say I'm consider small w, so I need to consider L power of 4. Okay, so just substitute 30.36 kilonewton per meter. L, the length, what is the length? The length of the beam? 5.6, right? 5.6. So 5.6, 5,600. Okay, 5,600. 5,600. Millimeter. Okay, 4. You got 300. Okay, E 1010 000 Newton mm squared. This one, what is the deflection here? L over 200. L is 5,600 divided by 200. Okay, just substitute. Okay, that value. Okay, this one. This is the allowable limit of deflection. So I required here is 66.1. Okay, 10 power of 6 millimeter power of 4. Okay, just that you need to convert because I okay, here in centimeter, in unit centimeter. Okay, so you need to convert. Okay, now I required is 66. 66. Okay, so we need to select I-beam that having slightly more than I required. Okay, 66 is here, slightly more. Dia centimeter, yours is in millimeter. Convert, saya rasa dapat berapa? Convert kan? 66.1 centimeter power of 4. Okay lah, tak ada masa, we don't have time. Okay, in this case, it shows 84. 82, sorry, 82. Why 82? Why 82? Because it is slightly more. But mine, we have 86. Dia 82. What size? 356. Oh, okay. That's why we need to convert. 6.6. W. Baik. Tiga lima enam satu dua tujuh. Okay. Okay, if you convert 66.1, okay, to centimeter, you get 6,610 centimeter. 6,610, that's why you need to choose slightly more. Okay, let's try another size. Okay, this one not fulfilled. What about this one? No, not fulfilled. I required is 6,610. Oh, you can choose 700. Okay, but bear in mind you have another checking that you need to perform too. This one only will satisfy deflection check because this is you use deflection check to get the initial size. So it will definitely only fulfill this checking. Remember, you still have bending moment, shear, bending plus shear, and then actually you have another checking that you are not learned yet. Okay, so consider that. So in order to consider that, why not we increase a little bit more? Okay, a little bit more, just to make sure that it will fulfill all the checking that you need to perform later on. Okay, so in this case, it choose the other size, not 305. It choose 357. Okay, it choose 356. Okay, you can try to choose this one. Awak boleh cuba tak ada masalah. You can try to choose 305. 305. Mana? 305, 127, and 42. It's still I I provided, okay, I put it here. I required is 610 centimeter. Or if you choose 305 times 127 times 42, okay, I provided will be 8,200 centimeter. Okay. Still, okay, bigger, still bigger than I required. You can check. You can choose that. Okay, or whatever I that fulfill or slightly more than I require. Okay, so that's all. That's all. I need you to see the difference. Okay, first using UK National Annex, second using approach from Eurocode. This example using approach from Eurocode. It consider lot combination. If you're using UK National Annex, means that the W here will be only the W, the imposed load. You just can add GK to 20.5 plus 1.8. That's all. Okay, that's all for lecture today. We will have another class. Okay, it depends. We will vote later on. Okay, ada soalan? Is there any question? Is there any question? Tak ada.
No, doktor.
Boleh faham ke tak boleh faham? Boleh faham tak? Actually, I have one more exercise. Tapi saya tak sure lah nak bagi ke tak. Sebab takut you tak faham kan. Okay, so that's all. Thank you so much.
Doktor,
Yeah.
boleh tak nak minta tambah masa yang untuk quiz tadi tu? Seminit je.
Alamak, kalau saya tukar nanti saya tak dapat kawan awak pun jawapan. Macam mana? Okay. Saya pernah edit lah. Saya pernah edit kan.
Doktor,
Dia hilang tau. Saya takut pula nak ni. Okay. Okay, kejap saya try. Macam mana nak tengok kejap Student answer. Saya tak boleh nak ni. Saya tak boleh nak, yang ni tak boleh pergi ke Excel. Saya takut hilang. Okay. Why not? Okay, okay, to be fair, semua orang buat dua. Okay. Saya allow lagi satu ni. There's one more assessment, but this one is you need to perform calculation. Okay, submit at least tomorrow. Okay, I put the due the due here as tomorrow. So 4 hari bulan 11:59. Okay. PM. Okay, tomorrow you need to submit. Okay.
Doctor.
Yep.
For today quiz, I couldn't save my answer. I already sent you to the message box, but you didn't answer me.
You already messaged you already messaged me. You already informed me.
Yeah. In the chat box and in your WhatsApp.
Okay. Okay, this is my decision. Please answer quiz number 2. I still will consider your attendance. Okay, if you submit quiz number 2. Okay?
Okay.
Just for your, okay?
Thank
It is
you.
for your training. It is for your own good. Okay? I know it will be a lot of work, but it is for your own good. It is like mathematics. You need to practice. Design is like mathematics. You need to practice. To master this subject,
Doctor,
this course, you need to do a lot of practice. Yeah.
can you share with us your slide that you are using?
Can what?
The
Can?
slide that you
Yeah.
are using during teaching us. Can you send it to us in the WhatsApp group
I
or?
already share with you, Moyet. I already share with you. Maybe you do not notice. I already share with you in the author.
Thank you.
You check your author, okay? Check your author. I already share with you this morning. Okay, thank you so much. Bye semua. Oh, okay. Before that, when you want the substitute class, during your your study, during your ini sekarang apa? Sem break or after the sem break. Remember, after the sem break, you only have 1 week before test. I am free during the sem break. I'm free during the sem break. Okay, during mid sem. Okay, thank you so much for your, I would say, enthusiastic. Okay. Tak ingat lah macam nak pronounce. Okay, I appreciate that. Siapa yang datang, okay lah. Ya, betul. 18 means that a week after awak masuk, ada 1 minggu je, and then the other week dah test. The other week dah test. Okay. Okay, thank you so much. Okay, one more. Siapa nak belajar dengan saya, boleh? Saya boleh buat kelas based on request. Saya boleh buat kelas. You nak buat revision, tak ada masalah. Okay. Last time saya buat revision, kelas revision. Cuma saya nak converse dalam bahasa lah. Saya pada my international student, you can come to my office and learn. Okay. Untuk kelas yang saya nak buat untuk revision adalah base kepada saya punya apa orang kata kehendak saya punya ni lah alternatif saya lah tapi saya nak cakap dalam bahasa. Pelajar boleh buat group 5 orang, 10 orang. Doktor, saya nak kelas, nak tackle this topic, bagi tahu. Kita boleh buat kelas, extra kelas. Kita buatlah sekejap je pun tak apa. Okay? So, bagi tahu. Okay, thank you. Bye. Alamak, saya lupa lah group project. Okay, nanti saya share dalam author dalam author saya share. Dia sama group project dengan yang section lain, semua sama. Kalau dah ada yang information tu share dalam group. Saya lupa sangat. Sama dengan section lain. Tolong share. Lecturer diorang dah bagi, tolong share dalam group. Boleh saya baca sekali. Sama je. Yeah? We will have the same project group as the other section. If you have the information, please share in our group. Okay, I'm totally forget about this one. Thank you for remind me. Okay, I'm totally forget. I thought I already shared with you that info. Okay, thank you so much. Bye.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doctor.
Selamat Raya
Thank you,
juga.
Doktor.
Thank you, Doktor.
Thank you, Doktor.
Thank you.